Thank you very much for coming up this morning. My talk will be a little bit away from the software because I will go on the hardware part. So for those who like hardware, that's the place to be. I will talk a little bit about the software that we run on top of the hardware that we develop. So my talk will be called Full Open Telephony Solution for Small Businesses. I'm Xavier Carcelle. I'm the hardware manager for a French-Canadian voice over IP company called Avencall. Some French people say Avencall. And this company is sponsoring the open source project called XiVO. And just for the story, XiVO is an acronym with the word voice, that is voix in French, so a play with letters. So just to introduce Avencall, we are based in France, 3 branches, and Quebec. One of my colleagues from Quebec, Nicolas, is there. He's currently working on redeveloping a library for SCCP, for the chain SCCP into asterisk. So he needs some help and support on that. So my outline will be explaining the XiVO project, explaining why we wanted to do hardware, and namely open hardware appliances. I will talk about the architecture, and talking about opening something, we would like to have a legal umbrella or something that can at least hold the copyright and the licensing for our hardware. Of course, hardware is not like software. You don't write line of codes. You draw schematics. You draw Gerber, and it's closer to a drawing or a picture than a line of codes. Well, I tried. It will cut the bottom of my slides. Not too many, but I can try. Is it better? Yeah? I explained the bottom part of the slides if they get cut. So the XiVO software component, basically it's a web interface for central configuration of asterisk. So we developed on top of asterisk a web interface that can help users to configure. We basically take all the features from asterisk, currently 1.6, and we have them available on the web interface. Along with that, we have a XiVO client in Qt that is running a CTI client connected to a CTI server on the asterisk server. And you can run that client on different platforms. Basically, that's a real-time interaction with the server that is useful for a large system. And we have a CTI server on the server side and an Android client. So that's how looks the web interface. That's an interface in French for the slide. We have several languages supported in our interfaces. So on the left side, you have the classical configuration of the IPBX, and everything goes through these interfaces. So we get cut a little bit. That's the menu that you get to configure the asterisk, and we have doing a provisioning made easier through our system. Also, we have a supervision features. So when you get on the interface, you can supervise the server. You can supervise the live calls and so on, the users, and you can connect that to a SNMP agent and get all these graphics into Kekti or Nagios tools that can gather all your SNMP traps and get. So on the client side, we have a CTI applications, and we have used that CTI to with different profiles. Basically, each client get connected to the asterisk or to the XiVO server with his profile, and you get some information coming back from the asterisk server. If you get super administrator, you will get the full vision of the asterisk server, and you will be able to, for instance, click and drop some calls through these interfaces running on your machine. You can also interact with the phone, the IP phone that is connected to your account. If you want to make a call, just click and drop on this on your account, and the phone will ring, and you can take the call through your usual IP phone. That's the screenshot of the XiVO client for Android. Again, get cut a little bit on the bottom of my slides. Basically, the idea was to be connected again to the CTI server over this client. We have been using that extensively with callback in France. We have a big insurance company that is using callback. So basically, you have this application running on your Android phones, and if you get towed away, or if you get a problem, you can run that application, start the application, and your profile will get connected to the central server of the insurance system that will dump and retrieve all the information concerning you, and they will call you back only when they get the relevant information concerning your profile. Okay, so advanced feature for the supervision profile in the XiVO clients. You get possibility of logging and interacting with the queue in, for instance, for a contact center. You can see on the bottom the queues in real time, and you can monitor this queue, get statistics in real time, and for instance, park some calls, override some features if you get, again, this administrator profile. Okay, so that's a short introduction for the software part. I move to the hardware part. Talking about this, sorry for some words are still in French, and I believe that's the only slide I get some remaining French words. So the software, you need to install the software on a hardware platform. So far we are using basically industrial motherboard with interfaces, telecommunication interfaces, and we split our hardware into 4 categories depending on the size of the system you want to run. The smallest one is the office for small businesses. That's the one I will focus on today. Then small businesses, you can go up to 300 simultaneous calls. And then we go upper with what we call the large business and the corporates. Currently, the corporate hardware we have is running systems with 2,000 phones on one site, with some load balancing between 2 corporates. So the idea was, so far, we're using existing hardware, motherboard, mainly from Portwell, which is a Taiwanese motherboard manufacturer, and adding some interfaces through PCI cards. That is doing a great job. Sometimes we have some issues. For instance, we had some RQ misses issues with some PCI cards, and then you need to understand the PCI architecture on the motherboard you buy to understand how is the RQ handled by the system. So sometimes we need to fine-tune the BIOS to get the right RQ settings, and we've been talking with Sean Ruffell from DGM about that to try to fine-tune. Then there were one-line patch on Daddy to fix that, basically trying to handle the bursts that you can get on the PCI cards, because some PCI cards or PCI buses are multiplexing or proxying different PCI peripherals. So the idea was, let's do the smallest one and start with the smallest one, targeting small businesses and replacing the office that we take off the shelf by our hardware. So the target is small businesses, in French TPE, très petite entreprise. 25 users. We picked 4 ISDN T0 interfaces, still massively used in Europe, mainly France and Germany. People like to have 64K guaranteed bandwidth for external calls. One FXO, one FXS. They want to use analog fax. They want to connect to analog PBX. So they like to have analog interfaces on that. Then, and I will go back on that, we are looking for what processor to pick. That's the usual core question when you want to develop a hardware solution running a CPU. And finally, extending the open source ID to hardware. We are not the only one, and namely, we are not the only one under this trademark called Honda, where now there is about 25 to 30 existing projects trying to develop projects under this legal umbrella. So the goal of the project is to develop a full open hardware IPBX, as well as the hardware and the software. I come from a hardware background. Before I was working on a hardware project where we developed an IP routers based on FPGA. So we were going a step further by having an FPGA and an open bit stream running on this FPGA. And yes, come in. This is Mark Spencer. Okay. And when you want to open up hardware, you can go very far. The idea then is to be able to make a community around your hardware and to have a gap between existing developers and new developers able to use your hardware and try to modify and so on. So that was one of the goals, was to open up, but still being in the range of being able to modify by some external developers. To serve a voice over IP appliance, running our solution and create a community about that. One of our goals is if that platform fits some needs, that could be one of the reference design to make an IPBX based on a x86 CPU and promote this trademark that I believe is a good one. So Telephony needs more open source projects, and namely in the hardware. And I quote Kevin Fleming from yesterday. He was quoting people, so I quote Kevin Fleming. And he said, well, before usual PBX were something that you don't touch for 50 years and you put somewhere and you don't know what is running and you don't want to touch it. Now the world is relying on IP and usual motherboard where you want to use telco cards. So we are not exactly in the same hardware schema. Now IP-based off-the-shelf, usually SBC or network equipment. Then you want to connect to telco through interfaces and analog, digital, and SIP interfaces that you will plug, that you will interface on your hardware. So just some recall. I just wanted to start with some closed word in the telephony world. So of course the telephony world has been closed, as well as in the old PBX world, quoting Kevin Fleming. I can quote Alcatel, Matracom, and so on. They are closed PBX. Analog interfaces, FXS, FXO, they are usually closed. Digital interfaces cards also. When I mean closed, I mean the design is closed, and usually the firmware running on that boards are closed. So if I go frame buffer, for instance, CPLD or FPGAs, they are usually running closed bit streams. The chip is an open design, but the bit stream running and configuring the chip is usually closed. Echo concealer, maybe you have a DSP, maybe the famous TI TMS 320, but then you have closed source firmware running on that. And I go into the very closed world, which is GSM, where we see some movement now. Of course, the baseband processor on a phone is very closed, and usually the core of the network is very close too. So, but there were some movement in the hardware, maybe coming from the software. We've seen lots of movement coming from, namely in the wireless environment, where open source software, I can name OpenWRT, were pushing hardware developers and companies manufacturer to open up some specification. Basically seeing that they had better software from the open source community than internally. So then they are now trying to integrate some open source people into their project. to be able to run a clean firmware from scratch and open up the specifications. So this movement of opening the hardware through the software, we've seen that from, I can name OSLEC from David Rose, I can name MISDN with Daddy and Colon Chip, I can name some movement in the GSM world with OpenMoko, which was an Open CAD files GSM phone. Who knows OpenMoko? Okay. Well, Aradveld, who was behind OpenMoko, did continue this movement with now GSM from the core network with OpenBSC and from the firmware running on the DSP on the baseband processor through Osmocom. And we can see that now he's able to recreate a full GSM network from the core network and from the mobile station side with open source, an existing hardware. Next movement will be maybe to run some open hardware to run the core network and maybe the GSM baseband processor. So when I'm talking about open hardware, not only I want to open up the schematics and the Gerber files and maybe the production files and the bill of materials, but I want also to try to give some documentation on how we did it, what was the mistakes, and maybe to help other projects to be able to not reproduce our mistakes. Trying to use our documentation or maybe manufacturing facilities. I've been 1 month ago in New York to the Open Hardware Summit. Second time they were Open Hardware Summit last year, and that year there were 500 people. And some projects now are gathering to go together to manufacturing facilities because they can assemble together, they can buy components together, they can have some lines of production booked together. And even if they are going with limited quantities of production, like hundreds, together they can make some movement and they can basically have some production facilities opening up their doors. So we want to publish our design production files. And again, we want to use that trademark, and I will talk about it later. So basically in a hardware project, you have some mandatory steps that you don't have in software. A proof of concept with the software can be very easily done, and then you can go to an alpha version and beta version quite easily. With hardware, you need to go from prototyping. Basically, prototyping can be assembling different reference design boards that you want to test. Once you get that boards connected together, you will want to run your software. You need some first alpha version of drivers, firmware, and so on. Then you want to target your first schematics of your final boards. Maybe you want to target the first Gerber files. Okay, who knows what is a Gerber and a schematic files? Okay, so I have a little bit of hardware audience today. The schematics is basically the link between every signal and pin you have on your design, and the Gerber files, the final drawing of the card, of the motherboard, of the board you want to produce, called the printed circuit boards. From this Gerber, you will export production files that you will send to the facilities for production. Along with that, you will have the bill of materials, the BOM, which is the list basically of all your components you want to buy, and that will be assembled, or in the manufacturing vocabulary called pick and place. Basically, it's a machine where you have feeders, and these feeders will pick and place all the components on your board. Basically, SMD. SMD are for the very small components. And then you want to target your first alpha version. Usually in the hardware world, we call that version A. The version A is usually, you need lots of debug. You need to wire some parts. You need to solder more components to try to have a working platform. Then you want to go to B version. The B version can be the one you can ship to developers, the one you can run the firmware, and you can have a stable hardware starting on. And version C usually the one you want to produce, where you can press the button for 1,000 and so on. So that's the last step. Of course, around that steps, you have different partners and ecosystem that you want to have. So basically, planning of the project, you prototype the hardware. Quite quickly, you want to prototype the software when you have like reference design connected together. You want to start running, for instance, for us, we wanted to run Asterisk quite quickly by linking our different reference board. We had to hack and do some alpha version of the drivers, DALI, to be able to see our interfaces as channeled for asterisk. Because we are talking about a CPU, you need to have a bootloader and a board support package. The schematics and board, the files I was talking about, manufacturing the first PCBs, and then availability, certification. That's a big step if you want to go commercial. So sometimes you need to certify several times. You need to go back to the certification facilities, and then casing, documentation, and so on. So one of the core issues when you want to run a board, what is the CPU I want to run? In our case, the idea was to be able to port easily all the work done on XiVO from the software side, which is basically x86. This is basically Debian packages that you can install. So XiVO run as a Debian package for x86. And I wanted to make the porting of that software smooth for the developers on the hardware platform. I can go ARM, I can go MIPS, I can go another architecture, but then I have all the cross-compilation issues. So by picking an x86 platform, I smooth my porting of the software on the hardware. So one good candidate was the EP8579, very nice name, from Intel. This is basically the system on chip from Intel that has integrated TDM controller inside. So that's in their catalog the system on chip for voice over IP solutions. When I talk system on chip, I mean, and I will detail that, a CPU plus other chips inside. It's a chip of chips. So Intel was quite surprisingly willing to play the game of OpenHardware and trying to be able to open up some specifications. And by having one of the first chip opening up specification for a voice over IP platform, I believe, and I see that from AMD, willing to open up more specifications, for instance, on the TDM bus. So it gets cut a little bit on the bottom. The Intel system on chip basically is an IA32 core. It's a CPU. Basically, it's a Pentium M running with 3 flavors of speed, 600, 1000, and 1200 megahertz. And then you have different blocks. Basically, you save chips by having this system on chip because you will get integrated in your system on chip the USB controller, the memory controller, the TDM controller, and so on. That usually are more companion chips that you can find on motherboard. On the motherboard, you will have a north bridge, you will have a south bridge companion chip called the chipset, usually along with the CPU that you're running. So on the left-hand side, you can see the details of each and every blocks that you have in the system on chip. And different interfaces on the top, and namely 3 Giga Ethernet interfaces. One of them can run PXE, so you can boot, start, and install from Ethernet 0 interface. So the architecture of basically the block diagram of our platform, basically on the left-hand side, you have a motherboard with the system on chip integrated in the middle, 3 Ethernet interfaces, 2 USB, 2 RS-32, and then SD card, 2 SATA drives, and 1 DDR2 controller that we picked on DIMM. So you can be able to change the DIMM on the DDR2 slots. And on the right-hand side, basically you have the interfaces, the 4 T0 controller. We are picking the colon chip XHFC4X4S. That is a chip that you can find on different PCI cards for T0 interfaces. And on the FXO-FXS, we're running a chip from Xilinx, originally Legirity, that is the LE89316, that is handling the FXO and FXS. These 2 right-hand side interfaces then get connected to the system on chip on the TDM bus through a slow bus. And of course, they had to be connected to the system on chip over with some interfaces like SPI parallel or serial interfaces, and some maybe GPIOs. Sorry again for that interfaces, for the cut of the slide. Basically, that you get the name of the buses with the core CPU in the middle. And what gets interested is that we have 3 TDM interfaces on our system on chip. So currently we are using 2. There is room for a third one. So one TDM bus for the Intel system on chip called HSS0 and HSS1 are occupied by the ISDN chip and the FXFX chip. And then you get the other interfaces. I guess if you have seen some hardware, you recognize the name. GPIO for input and output, SPI for a serial port, JTAG to debug the CPU, and so on. We will make available a JTAG interface on our CPU for those who want to go further on the CPU. So then we want to make schematics and boards. Then we had a question was, what kind of CAD tools we're going to use to be able to, for people to open up our files and maybe modify and play with them. At that point, we had 2 choices, basically Eagle, which is not a free, as in you don't need to pay tool, but there is a free reader and modifier for some parts of the design. So Eagle is quite a good candidate for us. And then KiCad. KiCad is an open source CAD tool framework developed by, in C++ by a French teacher to design boards. And our goal is to export our Eagle files to KiCad, so people can open up our files into KiCad and then only work in KiCad, which is, as I said, open source. I talked with the guy from KiCad, and he has now projects running and designed by KiCad with up to, I think, 16 layers PCBs. So it's done not only for small microcontroller cards, but also for large cards. We will publish our schematics once we have a stable version of our design. And like I said, Eagle allows us to read the files. We have a free reader available there. And also there is a ULP scripting language in Eagle that is quite fancy. Once you root, you get that kind of schematics, that kind of pictures. That's the FXFX board interface. And that's the one you want to export for the production. We decided to split it in 3, our prototype, so you can lower the risk of redoing the whole PCB. So basically, we did 3 PCBs, FXOFXS, ISDN, and the CPU. Then once these 3 connected together works, you just need to assemble your 3 design. That's also a good way for us to think about modular interfaces for our CPU interface. So concerning the PCB, it's going to be a 10 layers PCB. It's quite big, but the CPU requires quite lots of layers. We will manufacture in France. I extend France to locally. And personally, I believe we can produce locally. There is manufacturing facilities in Europe, in the US, and all over the place. So go to your local facilities and produce there. Go there and talk with the people there. There is some OpenHardware PCB facilities now. In the US, there is a company called CircuitCo that is quite open to OpenHardware system. And like I said, they can gather different OpenHardware projects to try to book some production facilities for them. I would like to do some documentation on the component origin because I've been working on the sourcing of all the components. And strangely, I don't see only components coming from China, but Malaysia, Japan, Philippines, Czech Republic, Germany, England, USA, so on. So that's for the hardware, basically the hardware platform we are doing. To run that, basically we have a full Debian distribution, like I said, on top of the kernel. We need some configuration buses for the interfaces chips, and we wanted to have a daddy driver so our channels can be visible into Asterisk as a normal channel that you can see into Asterisk. And of course, we had some difficulties to understand the internal TDM controller because that was merged with the system on chip from Intel is also holding a VPN encrypting engine, and there is a unique blob that they propose that is running the TDM and the crypto engine controller. So we have to split it into that part. So basically, our software to boot, it's cut, but it's core boot. Core boot is I will explain is an open source bootloader framework basically. Then we have the kernel with our drivers talking to Daddy, and then Daddy talks to Asterisk, and Asterisk talks to XiVO, and so on. You know the rest. So very quickly, the TDM controller, TDM, so handles the digital frames coming from and going to our digital interfaces. Basically, we have a global RX and TXQ per channel, and we do channel packetization like is it done usually on TDM cards. We do 1 milliseconds chunks of packetizations, which is the standard for usually for Daddy. And so that's kind of packetizations and fragmenting of our TDM packets then can be handled by Daddy using that chunks. Concerning the bootloader, we have a flash, a 2 megabyte flash, where we will store the BIOS, the MAC addresses for our Ethernet range, and the serial number for our device. That will be stored in a non-writable part of our flash. Of course, we are open for people that would like to reflash the BIOS and so on, but we don't want people to break easily our platform. So we have been doing a support for core boot for our design. Actually, the difficult part when you want to run core boot on a platform is usually the DDR, the RAM controller, where you need to get some specification on that. To flash it, we use FlashRAM. It's a tool in the core boot framework. And we are currently pushing the support upstream into core boot for this platform. For those who followed core boot news, AMD announced that they are now supporting core boot on all their products, and namely Portwell, which is a manufacturer using AMD now, supports core boot as a free or open BIOS or bootloader. So basically, no, I just
Xavier, can you just repeat Doug's question, please?
Question was, did we use a reference design from Portwell, and how is Portwell in the landscape of our design? Portwell is only our existing provider of motherboard, nothing related to our design. And I just named Portwell as a company supporting core boots because they use AMD for their motherboard, and they announced as a commercial agreement that they support core boots for their motherboard. But that's two separate topics. Yes, we design it. So on the bootloader, basically, usually core boot runs as on the left-hand side. Core boot, like I said, is not a BIOS, is a bootloader. Then they will jump and load a payload that will, how many minutes I have left? -5? 4 or 5, good. So basically, core boot is then stored in a RAM or in a flash space. The CPU starts, goes to a very specific address, and then this address jumps to the payload, and the payload is the actual BIOS that you want to run, and this BIOS holds the controller, the minimal controller like network interfaces controller where you want to run PXE interface and so on. we have a small file system in core boot called the CBFS that is quite useful for us to run several partitions in our flash. And namely, the non-writable flash partition can be stored in this file system. Follow core boot, that's quite intensive software project currently. So our goal on the software side, validating the boards per package to submit it upstream. Of course, we want this platform to be off-the-shelf supported with the DADI drivers that we are finalizing, some kernel drivers that we need to develop specifically on the TDM interfaces, the core boot patch, and all this will be available on our Git branch for the hardware projects. In the few minutes I have left, I want to talk about licensing. Of course, we have several questions about, are you guys crazy about opening up a PCB design of a hardware platform? Maybe you are crazy, maybe not, but we don't want to be copied for free, and we get protected by a trademark. So this is not really a license, it's more, you can see more like a label or a trademark that you registered. So you need to accept the rules of this trademark. Once you get these rules, on the right-hand side, the consumer, they will be able to find your unique identity in this trademark, for instance, a sticker or a label or a new design. With this unique registered ID, they can go back to the repository of your project on Honda and get the files, connect to the designers, interact with the project, and maybe modify that to get another unique ID in Honda, because they need to respect the rules behind that. You can go on the Honda page, and you can see there are several projects, from non-commercial projects coming from maybe the CCC in Berlin. They want to develop the robot for the moon. They are developing that under Honda. And you can see artistic project, but you can see also commercial projects starting to be under this legal umbrella. Basically, in the license landscape of OpenHardware, you have three movements now. I call that the American movement, with the people from Make Fair, Wired, and the people doing that. They are proposing an open source license for hardware. Honda with that project, and the CERN in Geneva that is proposing also another license for their hardware platform. Currently, these three licenses tend to merge into one in a close future. So the PCB, like I said, CAD tools. We have about 30 pages of schematics. It's a 10-layer PCB. We're going to be produced locally. We want to have some statistics and to open up the bootloader for installations. In conclusion, we want to replace our XiVO IPBX Office products. We want to have an open design hardware under this trademark. We want to create a voice over IP community. We are very willing to interact with people if they want to make other interfaces, they want to modify the design. Basically, the idea is to have a reference that is well known by people, that is running asterisk, that can be modified with the documentation, and that can open up will for people to prototype, design, manufacture hardware in the voice over IP world. We will get the files available when we will release the board in Q2 2012 after final prototyping and certifications. Finally, our blog.